Transportation in today's world is a major contributor to the impact of humanity on global climate. In the United States, major pressure is placed on automotive manufacturers through CAFE and EPA standards to push vehicle and propulsion systems to be as efficient as possible while reducing toxic and greenhouse gas emissions. This leads to substantial investment in onboard vehicle equipment and capabilities and almost single handedly drives the interest in electrification of the automobile. Today's cars are more complex than ever and require even further refinement in order to meet stringent upcoming industry standards. In parallel, through vehicle to vehicle and vehicle to infrastructure connection, your car will soon be able to talk to its surroundings, other cars, traffic lights, and even lift bridges in real time. Also, in parallel, vehicles are now able to drive themselves in limited fashion autonomously through technologies like adaptive cruise control. Although much of the effort is spent on existing inefficiencies of the vehicle itself, many broad level improvements are possible. For example, vehicles driving down the road today each manage their own aerodynamic load, or the air that is being pushed when the vehicle moves. Like you see in NASCAR, if vehicles drive very close to each other, that load can be shared between vehicles. This can lead to as much as 10% overall energy savings, which in the automotive energy world is a big deal. The obvious issue, of course, is that the following distance required for any energy savings is unsafe at any speed. Since emerging tech vehicles can now communicate with each other and drive themselves, it appears as though the possibility of high-speed, autonomously controlled connected platooning is possible. The concept of platooning in vehicles has been around for decades, but it's not easy to do safely. For example, specific messages are required to distribute information from car to car in order to understand forward-looking obstacles, any real-time changes in speed and gap between vehicles. This project aims to identify characteristics like communication lag, vehicle reaction time, and vehicle dynamics in order to establish the algorithm that will eventually make platooning maneuvers possible on our public roads. If we can understand the ideal platoon configuration based on each vehicle's individual performance and drag, even more energy can be saved. Automation technologies can be a breakthrough for the other energy-saving technologies that are of interest. For example, this 10% savings means electric cars can drive further without extra batteries. An analysis of a fleet of 8 Michigan Tech connected Chevrolet Volts and several other vehicles and platoons at varying speeds in closed course conditions will show us exactly how to implement a real-world solution to this challenge. Thank you.